Hi, I'm Alan Jenson. Nice to meet y'all. I'm an engineering manager at Paxos, where I work on our settlement technology. I joined the company around 2018 and have been looking to make the financial system more efficient. Primary driver. I apologize in advance. This talk is riddled with corny segues. So here goes the first one. And wouldn't you have it, the theme of the talk is efficiency, specifically payment netting efficiency. I'm really happy to be here at FinTech DevCon 2022. I was lucky enough to spend some time with some of the Moov folks last night. I really think what they're putting on here is excellent. They're great people. I recommend speaking with them while you're here. But yeah, FinTech DevCon. It's my first time in Colorado. Quick show of hands, who's been to Colorado before? Wow, that's a lot of people. I mean, maybe a lot of people are from Colorado, which makes sense. Let me do another poll. How many people here have been to Colorado for skiing? Okay, sizable amount of people. And now this is my segue into talking about skiing. I actually went on a ski trip. It's not really relevant to the workshop, so don't worry about it. But I went on a ski trip back in February. Had a group of 8 people. Some people pitched in for beer, some people bought the lift tickets and the Airbnb, the housing accommodations. And we all settled at the end of the day. Everyone was square. It doesn't really matter how we did that, just as long as you can trust me that we did. There's no way that 8 strangers, 8 skiers, hold the secrets to payment netting technology, unless they do. And they do. You see, there was trouble in paradise. 3 big problems riddled our merry bunch of adventurers. The first problem was that each skier had a certain amount of payment that they would be willing to accept from everyone else. I don't want to handle hundreds of thousands of dollars of my friends' money. No, just give me what I need, please. Another issue was that there were some international taxes. We had a very multicultural international group, and when some people went back to Argentina, some people went back to Greece, some people went to other countries, paying across borders, especially paying US dollars across borders, has some pretty interesting tax implications. So there was a cost for every dollar spent between different parties. And the third issue is that some of the people who were skiing were also feuding. And after skiing, did not want to speak to each other, did not want to see each other, and certainly did not want to be paid from each other in any respect. So, trouble in paradise. I'll go over to the big picture. I'm very proud of this. Anne, Beth, Cole, Dave, Eve, Fran, Gail, and Hank. The black lines here just have that standard capacity constraint, where you can't pay more than X dollars across this relationship. The purple lines here mean that there's some sort of cost for paying, presumably taxes, or it could be something else. And then the pink lines here, I have to stay on the Moov branded colors, a part of the presentation. So they would be red otherwise. But those red, pink lines are people who don't want to face each other for payment at all. So what do? It poses an interesting problem. The problem is, how can we novate obligations to reduce the cost of payments? And this requires 2 definitions to really be a good problem. Let's do novate first. So novate is to replace one set of obligations with another set of obligations that have the same economic impact, but are hopefully better and have better efficiency. Maybe I should have done obligations first, but here we go, obligations. This is a promise to pay at a later date from one party to another, some amount of dollars. And what I'd love to do now is to go around the room and ask, how can we reduce the cost of payments? No, this is not how can we best reduce it. This is what are some ways, even if they're a little bit mouth breathing, for how we can make the graph better. Any ideas so far? It's a doozy.
Maybe not settle immediately?
Yeah, I mean, delaying will certainly, well, giving you a chance to process the problem and make something better helps. I mean, at this point, everyone's back in their home countries anyways, so there's been some delays. But what do we do now? Go ahead.
I was thinking like a one-to-many, like one person pays everything and then.
That's a good one, and we'll definitely get to that later in the talk. Thank you. I'll buy you guys some time, and to do that, let's jump into the code to see the actual software definition of the problem we're trying to solve. So we have public class Novator. What does a Novator do? It novates. It takes in a problem, and problems have obligations, and the Novator is in charge of giving a new set of obligations that have the same economic details. And in this case, we have a functioning implementation right from the onset. Congratulations, everyone. You guys can go. Presentation's over. No, we have a functioning implementation right from the beginning. And that implementation just returns the obligations that we start with. It's certainly true that the same obligations that exist have the same economic results as the obligations that already exist. And our task in this workshop is to change this Novator to make it, well, we'll see in a little bit, but the best it can be. So with that, with the time that I bought you guys, I'd love to go back to the problem. Any more ideas on how we can not do the best, but at least at this juncture, just improve?
Can you flip back to the visual?
Which, you mean the picture?
Yeah.
Yeah.
Set up some sort of like, I don't know, central, I don't even know what to call it.
Maybe a central counterparty?
Yes,
Yeah.
perfect.
That's a great idea.
Are these all in different countries?
Yeah, you can assume that everyone here went back to one of 8 different countries themselves. That's not really true, and honestly, there's some hyperbole in the story, but it made for an interesting premise. Okay, go ahead. Sorry.
I was curious, so the delivery mechanism, is it like the same? I mean,
No, like you can imagine that they could be different, right? Like, so maybe this relationship has to be paid over ACH, which is why it's cheaper, whereas this needs to be like has a wire over it or something, which might make it more costly. So, but that's a really good call out. Thanks. Okay, heard a couple good ideas. Some good ideas, well, actually they're not great ideas, they're okay ideas. Some okay ideas that I came up with on the fly, were one, party pair netting. In this world, you look at each relationship, look at every obligation across that relationship and say, let's collapse this down to be just one obligation for these 2 people, right? I'm sorry, I forgot your name. Matt. If Matt buys me a candy bar, and then I buy Matt a candy bar, and Matt buys me another candy bar, and we just keep buying thousands of candy bars for each other, we still probably only need one payment to make that real. And if you do that, you can get to a point where you have n squared over 2 obligations, where n is the number of skiers. Definitely going to be better. It's still not perfect, but I think it will improve. And another option is kind of a mouth-breathing, greedy algorithm, where we look for any pair of dollars that we can replace with another dollar in another obligation or across another relationship to make the to minimize or just to get that optimality $1 better or 1 unit better. You can then expand that to say, okay, instead of looking at pairs, I'm going to look at triplets or quadruplets, et cetera. But eventually, I think you're going to run into, before you run into the constraints of the actual problem itself, your CPU is just going to burn out if you try to write this in code. I also want to up the stakes a little bit. How can we novate obligations to minimize the cost of payments? How can we be the very best like no one ever was? Some chuckles in the audience. Yeah, so how can we be the best? And it's worth highlighting that best here, most optimal, is actually not an outcome of this graph. It's not to say, like, hey, the best thing is for Dave to pay Cole, because best is actually a number. You can say, what is the total cost of paying all of the payments, of paying all the obligations? And if that total cost is the same across one set of solutions versus another set of solutions, they're both equally valid. I think we also need to redefine how we're looking at the problem. I deliberately misled you earlier. I told you not to trust me. Instead of viewing these as skiers, let's view each party here as either a source of money into the system or as a sink of money into the system. And you can do that by saying, sum up everything you owe, sum up everything that you are owed. If you are a net ower, if you have more obligations than you are obligated, you are a source of money. And if you have less obligations than you are obligated, you are a sink of money. Money is going into you. And then with those two, we can actually draw a very large imaginary circle across this entire graph and call it a closed system. There's no money being injected here, and there's no money escaping. All the money stays between the little smiley faces that you see on the screen, which is nice. We can exploit that.
Minus interchange?
Say again?
Minus interchange?
Oh, minus interchange. Well, let's say like, that's a good point. No, thank you, I appreciate it. So now we get to central counterparty netting. And sorry, I forgot your name in orange. Andrea, you were getting here earlier. Thank you very much. Yeah, so the central counterparty netting model is I'm going to make a new party, instantiate a new object, and add that person to the graph, the central counterparty. And everyone can now forget about their relationships with each other and only interact with this CCP, central counterparty. And this is great. I want to just highlight that this picture is very pretty. I actually think this picture is prettier than, whoops. This picture is prettier than this picture. It's also a lot prettier than the next picture that I'm about to show you. But it starts to deteriorate if the relationship between the parties and the CCP starts to sour. If these arcs, we're calling them now, let's define a new term, these arcs, have a cost to them. Maybe there's some sort of tax, or maybe there's some sort of administrative cost. In practicality in the industry, you might make a new legal entity to deal with this sort of thing. And that has costs with it above just being friends with everyone. So let's go on to that ugly picture. The min cost network flow. In this, we're trying to use graph theory and software to find the most optimal set of payments and allow each party to pay their contribution to that minimum set of payments to satisfy the obligations. And the formulation is more complex. It requires more software and more logic, but the result is better. So let's talk about the formulation. We've already talked about considering the network as a graph where flow leaves sources and enters sinks. We talked about how arcs between those nodes, the relationships, the lines between those people, have capacities at the max amount of dollars which someone is willing to accept from another, and as well as costs. Costs being, well, here are the taxes, right? Worth highlighting that these are unit costs, not absolute, hey, if you go down this highway, you must pay this amount of toll, but rather you pay this much per highway you drive, taxes. I didn't do a great job explaining that. Like, it's like taxes, like you pay income tax. It's a fraction of the total going through it, right? And then we're going to solve in bold and make obligations from the answers. And it's no coincidence that solve is in bold. That is the next portion of the talk. So how do we solve this? Great, we have this awesome formulation. We know what we're trying to do, yay. Okay, now how do we get the answers we want? There's an algorithm that's been around since 1947, I believe. It's called simplex. And if you're familiar with optimizations and constraint solving, you'll probably be familiar with simplex as well. It works on one key observation. And that observation is that any objective function, every objective you could possibly have to optimize, will be at a vertex of some geometric shape as long as that shape is convex, meaning it doesn't have divots. A divot here meaning like you'd find a local maximum or minimum. As long as it does not have divots and it is convex, you can find an answer at a vertex. So let's do a couple experiments here. If I'm trying to minimize y, how do I do that? Where's the minimum y within that triangle? Anyone from the audience want to go ahead? Yeah, and again, it's worth highlighting that there are actually many answers for what is the minimum, right? The answer is true anywhere along this line, actually. But it's also true that that answer is at the vertices, right? This is one answer to it, and this is another answer to it. And if you were trying to say what is the part on that triangle which minimizes y, two people could give you two different answers that are both optimal and both right. Actually, they can give you infinite answers because it's a line, right? But yeah, just bringing back that point that optimality is a number. It is not a result. It's also worth talking about how this algorithm performs. And it's on the order of v squared, where v is the number of vertices in the problem. And I'm going to switch from pretty pictures and Moov branded colors to actually painting diagrams in the air with my hands to illustrate that complexity. So imagine you have one vertex. Simplex is trying to find which move to make from that vertex. And to do that, it will look at every vertex around the vertex it's currently on and see where it can drive the objective function higher. But then that move is an n operation. You're at a vertex, you have to do basically an operation per other vertex next to you to find the next one. And then you move to the next vertex and then repeat. If you do that enough times, you eventually find you're at n squared, right? Or sorry, let's call it v squared, I'm saving n for another variable later. And this makes it a good solution for small data sets. It also makes a good solution for asynchronous processing. And it's worked really well and served the industry pretty well for quite a few years. But it's not the best. It's the best for a lot of other applications, but not for this specific problem. There is another way to solve it called cost scaling push relabel. And it's a variant of push relabel, which probably deserves its own explanation. Do you know that if you're cruising through, well, we talked about Reddit earlier, if you're cruising through Reddit or Facebook or social media, in addition to the posts that say like one cool trick that doctors don't want you to know, you'll also see sometimes that like maze of cups where you see like one cup up here, one cup down here, some pipes going between the cups, and it's like which cup fills up first? That one. If you think about how your brain works to solve the answer to those brain teasers, that is effectively how the push relabel algorithm works. It says, I'm pushing through as much flow as I possibly can. Where does the water flow up? Oh, okay, this bottom cup is full. I'm going to come back up to the cup that fed it and see where that cup feeds water next. Oh, all the pipes going to that cup are full. And it effectively forces flow through the system as fast as it can in a thought experiment to find what the max flow is. Critically, max flow is not what we're trying to solve here. We're trying to min flow. And that requires another step on top of that, on top of that push relabel algorithm. And that step is to consider a logarithmically scaling price function, which says at every step, well, what is the next price I need to handle? How do I shift the problem to be cost optimal as well? I'm not going to get into it that deeply, honestly. I encourage you to look at it in your own time if you're interested more. Because it competes with the next slide and the thesis of this presentation, which is, I'll spoil the punchline, this stuff is easy. Let's go through the runtime complexity of the cost scaling push relabel algorithm. It's O(n squared m log nc, or n is the number of nodes, think about parties, m is the number of arcs, and c is the cost of the largest arc. And this runs lickety-splits. It's very fast, so fast that you can run it in production with live data. And that's a game changer. So this was 1990, or mid-90s, I think, where this came out. Fast forward to April 2021. What happened? Well, some great developers at Google made an optimization library. Well, the optimization library had already existed, but they gave it a Java port, and they posted it on Maven Central. So now, without using a large, bulky third party and paying out the ying or using complex software, we can solve optimization problems that solve the problem of payment netting in a very easy way. The next part of the talk, or not talk, of the workshop is actually diving into code, running this for real to show exactly how easy it is.
Did they change the algorithm at all, or they just?
No, it's very faithful, and it's interesting. In addition to the primary sources from the cost scaling push relabel alg, if you type in like the name of that algorithm, you'll get references to the actual library for how good the documentation is and how well they followed it. It's really well done. So what? Like, what have we learned and why be here? A few things. One is that min-cost flows are great. They solve problems and they make things more optimal. Number two is that the cost scaling push relabel algorithm is really snappy and can make your optimizations run faster than you may have previously expected. And number three is it's really easy to do this now, much easier than it was in earlier times in history. And it's available now for developers all across finance. And I encourage you all to do it if you have suitable use cases. Thanks. I'll also throw in that my name is Alan Jenson. That was a joke. And my email is ajenson@paxos.com. Obligatory, I'm hiring, we're hiring, everyone's hiring post. And with that, we can move into our dev section, where we'll actually go through the GitHub repository and implement one of these min-cost flows for that merry band of 8 skiers. Awesome.
Can you tell us a little bit about how you're using this at Paxos without?
Yeah, so I'm trying to be very careful here. They want to prevent you from doing product pitches and demos. I can tell you that I work in settlement, and one of the areas that I've been very focused in is the settlement of U.S. equities.
Okay.
So how do equities, how do you make the least amount of movements for stocks based on trades that are executed at exchanges? And if you replace the skiers with names of large investment banks, you can get some really nice efficiency out of these algorithms at scale. Go ahead.
Which skiers were did you go to?
I went to Zermatt. The Colorado thing was actually a complete red herring. I've never skied in Colorado myself. But I did go skiing. Go ahead.
You can save this question for later if you'd like.
Yeah.
I was wondering if you have any trouble with, take the 8 skiers.
Yeah.
If you use this algorithm to help come up with the best solution, you're having to ask someone to send an amount of money to someone that has no correlation with money they spent on the trip.
Yeah.
So is there a problem there giving them instruction to do that when it isn't the amounts that they expected, and they aren't sending money to people they expected to send it to?
Yeah, so that's a great question. The amount of money is actually not very contentious. It's guaranteed, because you're either a source or a sink, it's guaranteed to be less than you were initially going to from your initial obligations, right? And it does. Let's go back up to the picture. Suppose you have no purple and you have no pink on this graph. If you're in that situation, everyone's flow out of them is actually the same as it would be in that CCP model. You are actually giving the minimum amount of money out of yourself. Well, sorry. You're never going to be giving more, and you're going to have the same obligations, the same economic impact at the end of the day. But if you have no purple or pink, you are guaranteed to have the same total amount of payment at all. The total obligations given. There's a difference between total obligations and flow through you, right? So suppose I owe you $1. You owe, sorry, I forget your names again, but Matt, a buck. Seth. I give Seth $1, Seth gives Matt $1, and also I owe you $1. I might give you $2, and Matt and I are feuding. I might give you $2, you might give one of those dollars to Matt, and at that point, the flow through you is still like $2, right? But you may expect that you want to minimize that, because while I'm giving you that $2, there's probably also a cost in me giving it to you, right? So your total is probably the same, but you also want to minimize the flow through each of these parties. And when you have no red or no pink and purple, the flow through each party is actually just their obligations. Does that make sense?
Yes.
Okay, thank you. Question in the blue, what's your name?
I think I was kind of like, confused.
Yeah.